Hello, I'm Marvin. I'm a second-year PhD student here, working with Peter and Sergey. Broadly speaking, my interests are in model-based reinforcement learning and representation learning, especially with applications to robotics. So today I'll tell you a little bit about some of the previous work that I've done that was at ICML this year on actually combining model-based and model-free reinforcement learning. So some motivation. Model-based reinforcement learning is really great, as you've already heard from a few people, because it's really data efficient, and you can learn policies from scratch using a really small number of trials, which is great, especially for real-world systems like robots. But modeling suffers from bias when you try to consider these really complex systems with dynamics and costs, and if the bias is too high, then your learning will fail and your policy won't be any good. This is in contrast to model-free reinforcement learning, which can handle arbitrary systems with really complex dynamics and costs, but it's going to be way less data efficient. So the question we asked in this work is, can we integrate these two approaches and try to combine their respective benefits? The short answer is yes. And I won't go into details, but you can find out how we did it in the paper. But let me just show you performance on one task where this PR2 robot actually tries to learn how to shoot this hockey puck into a goal. So we're using a model-based method for this. We did try this, and it didn't work because it can get to the puck really reliably because that part's easy, but hitting the puck is really hard because there are contacts and dynamics that are really complex. So the model-based method's going to fail. And the model-free method's just not data efficient enough to learn reasonably quickly. And my colleague Yevgen here doesn't want to reset this hockey puck thousands of times just so this robot can learn this. However, our method can successfully learn how to hit this hockey puck with only a few number of trials, with about 200 trials. And it successfully combines data efficiency from model-based methods with final performance of model-free methods. Thanks.
Hi, I'm Sandy Huang, and I'm a fifth-year PhD student working with Peter Beal and Anka Dragan. Broadly, my interests are in developing methods that provide insight into what exactly an agent or a model has learned. So this is essential for building trust, enabling seamless human-robot interaction, and for deploying robots in safety-critical situations. So for example, if you need to interact with another robot, you want to be able to anticipate what this robot is going to do in a variety of situations in order to interact with it. Or if you're about to deploy a model, you want to know beforehand which situations this model might act incorrectly in. So I'm going to briefly talk about two projects along these lines. In the first project, our goal was to help users quickly learn to correctly anticipate a robot's behavior, even in novel situations. And we focused specifically on autonomous driving. So when humans see this yellow autonomous car driving around in different scenarios, they naturally get a better and better understanding of how this robot acts and what trade-offs it makes. And so in this work, our goal was to speed up this learning process by optimizing for the most informative examples of robot behavior to show the human. In other work, we showed that policies that are trained with deep reinforcement learning are vulnerable to adversarial examples, which are inputs that are specifically constructed to force misclassification. For example, in chopper command, the adversary is able to make a fully trained policy crash by changing one pixel in this mini-map of the game to cover up the enemy. And this is a black box scenario where the adversary doesn't have access to the trained policy. We also showed that dormant adversarial attacks are possible, where in this case, we fully trained an agent to solve a maze. But then you can corrupt the agent's memory by introducing a single adversarial example and get it to actually go to the incorrect goal. Thank you.
Hi, I'm Rohan. I'm a fourth-year PhD student at Berkeley. I'm actually currently working in programming languages, but I am hoping to switch into AI or ML. And working on that now. I've taught a few AI/ML courses before, which is how I managed to get in here. So my current research is actually about trying to apply programming language techniques like program synthesis and partial evaluation and a few others to improve the sort of computational efficiency, just like speed, of inference algorithms for probabilistic programs, which is sort of this nice way of building generative models. Yeah.
Hi everyone, my name is Andrew. I'm a first-year master's student at Berkeley. I work in Peter Abiel's group, and in the past I've worked on some projects. The first is trying to learn robot behaviors from human video demonstrations, and I also worked on transferring policies from robots with different physical configurations. So today I'm going to be talking about our video learning project, and so this is kind of a summary of our results. So on the left, the first column is one of many human demonstration videos that we recorded, and the robot is given these videos ahead of time. And at test time, the robot sees a new environment that it's never seen before, so that's the second column. And our model tries to predict what the expert would do in this new environment, and that's going to be the third column. And finally, the robot uses reinforcement learning to try to match the predicted behavior. So the right is the autonomous execution of the robot in this new environment. Thank you.
Hi there. My name is Garrett. I am a fourth-year undergrad studying CS and math here at Berkeley. I'm very fortunate to work in Peter's lab, Professor Abiel's lab, with Aviv Tamar. And we are interested in deep reinforcement learning with applications to robotics, and in particular, the problems I work on study policies that plan and their generalization properties. So one result you might have seen is value iteration networks. This is presented at NIPS last year. So one motivation for this is that a lot of policies in reinforcement learning are just reactive. So they essentially just learn how to map observations to good actions based on the experiences that they've had in this environment. But some problems actually require you to build a plan in order to perform well in the task. So for example, we considered a grid world environment where you're just learning to solve a maze. And this actually does require some planning computation. So the key technical insight here is that you can basically bake value iteration into a convnet with standard convolution and max pooling operators, and then it actually learns this differentiable version of value iteration that we can use to plan. And we showed that it generalizes better than a reactive policy. Some other work, hindsight MPC. So model predictive control, recall that it builds a model, and then it uses that to solve a sort of a short horizon planning computation at each time step, and then executes the first action from that. The problem with this is that although we need the short horizon in order to maintain like a real-time controller, but that's not going to enable us to improve over episodes. And so we actually learned a cost shaping that will encourage this short horizon planner to sort of mimic a longer horizon planner that's executed offline after the episode is over. And currently we're working on combining some more traditional robot plans, motion planning algorithms with learning-based approaches via guided policy search.
Hi, I'm Yang. I'm actually a third-year PhD student at UIUC, and I'm just finishing a research intern at OpenAI. And my current research interest is the RL algorithms. So specifically, I'm interested in explorations in RL and Bayesian RL. So the idea is to incorporate the parameter noise to the action noise. So one work I want to mention here is a ICLR paper last year, and we derived a faster algorithm to improve the DQN training. And what we do here is like we derive a upper and lower bound for the Q learning, the Q values during each step of training. So here's the results on the Atari benchmark. It could be shown that we could improve almost all the results on the Atari benchmarks. So it is not quite common in the Atari experiments. And another research work I want to highlight here is a recent work called Staying Versional Policy Gradient. So basically what we do here is like we use a Bayesian policy optimization framework and derive it to a Bayesian inference problem. And then we use staying versional gradient descent method, which is a recently developed method to solve this problem. So with this algorithm, you could see that we could achieve like diverse policies here. Also, we could have a faster convergence compared with single particle algorithms. So here are the plots for the state visiting plots here. You could see that almost all the policies are discovering different parts of the environments. So that's my recent work here. So thanks.
Hi, everyone. My name is Richard Chen, and I'm a research scientist at OpenAI. My major research interests include exploration in reinforcement learning and also multi-agent reinforcement learning. The first research project is also along the line of improving DQN. As we know that DQN is trying to estimate a Q function based on the sample transitions. This is an frequentist approach, and typically, Bayesian approach can achieve better performance compared with frequentist approach. However, in high-dimensional settings, such as Atari environments, explicitly doing Bayesian reinforcement learning is actually very impractical. So we use ensemble methods to approximate some of the Bayesian reinforcement learning approaches here. So with a Q ensembles, then we can approximate sampling Q functions from the posterior distribution of the Q function. And the different Q functions can provide uncertainty estimate about the Q values at each state and action. So we ask the agent to take action by balancing the reward that it can get and also the uncertainty of the Q function at each state and action pair. And so the result is summarized on the plot over there. The baseline, including the black dotted line and the purple dotted line, are our internally well-tuned double DQN and bootstrap DQN model. And our method is actually provides 3 algorithms, but the most important one is the green. And this shows the weighted normalized learning curve across 49 Atari games in using 40 million frames. And the second project is a multi-agent setting where we chain agents that learn how to model the opponent's learning behavior. And in a very simple environment where different colors of agents pick up coins, if they pick up their coins of their own color, then they get reward for themselves. Instead, if they pick up coins of the other color, then they will incur a loss on the opponent agent and also a positive reward on themselves. So we can show that independent agents will pick up just random coins irresponsible of the opponent's behavior, while our agents will be able to learn to pick up coins of their own color and not incur a loss on the opponent. Okay, that's all. Thank you. Later.
Hello, everyone. I'm Haran. I'm a third-year PhD student at UC Berkeley, working with Peter and Sergey. I'm interested in general model-free RL and model-based RL and some combination to meta-learning. I'll describe a research that I did about exploration in reinforcement learning. Exploration is a difficult topic because in the case of sparse rewards, it's difficult for an autonomous agent to figure out the true rewards exactly without exploring the state space very efficiently. And here's a very simple fix to it. You just have a bonus reward, which is a coefficient beta divided by square root of the count n of the hash code phi of your state S. So what does that mean? It means if you visit a state very infrequently, then there's a bonus for you to encourage to visit that more often. And why is there a hash function? Well, in the case of a high-dimensional state space like images, it's difficult to get the exact count. And a very simple fix is to encode a state as a hash code, and then we can count it. And this simple method actually achieved about state-of-the-art results on Freeway, Frostbite, and Solaris, which are 3 Atari games. And here I will show you one example. So in the case of Frostbite, here's an agent trying to get rewards by jumping into the ice sheets. And sometimes it actually explores to get to a different place, which is the cave, where it has higher reward and it gets to the next level. Some of my recent work is on energy-based policies for reinforcement learning, also called soft skill learning, and my colleague Thomas will talk about it.
Okay, hello everyone. My name is Tuomas. I am a 4th or 5th year PhD student working with Peter and Sergey. So I'm interested in model-free RL, and as Haran mentioned, I'm focusing on soft skill learning currently. So in the following 1 minute and a half, I'm going to teach you what's soft skill learning. Here is something that you have seen before. So this is the standard Q learning update, where we update the Q value of current state and action to be equal to the expected reward plus the maximum of the value of the state where we land, or the value of the state where we land, and that value is given by the maximum over actions of the Q value. Soft Q learning is different only in one way, so we replace the maximum with the soft max. And the intuition here is that if there are several actions that are all equally good or roughly equally good, we want all of them to contribute to the value. So think about if we train an agent to walk, there are multiple ways how you can walk, and for any given state, there are multiple actions that you might want to take. And this soft max formulation allows us to account for all of those options. So similarly, the policy is stochastic, and it randomly samples among these good actions. Here is a video showing how it looks like when you're actually trying to walk in all the possible ways at the same time. So as you see, sometimes it hops, sometimes it walks, sometimes it does random things, but it's still clearly moving to the right, and it's stable. This might look funny, but there are reasons why this is actually a good thing, but I don't have time to talk about those right now, so please come to me and if you want to hear more about them, or check out our paper. Thanks.
Hi everyone, my name is Tianhao Zhang, and I'm a second-year PhD student here at UC Berkeley, advised by Professor Peter Bill. My main research interest is in designing learning algorithms useful for controlling real robotic systems. So for that issue, apart from sample efficiency and using raw sensory inputs, an important aspect is the robustness of the policy. So for that purpose, we combine model predictive control with guided policy search, which is a framework which is a model-based sample efficient framework known for learning deep control neural network policies from raw sensory inputs. And here we demonstrated in simulation that the learned policy is robust against a range of model errors and environment disturbances. And here I show an example which is currently requesting access now, unfortunately. So basically, using the baseline methods, the quadcopter syncs with 0.05 kilograms mass error applied, whereas using our method, the quadcopter flies through and is able to handle both the training scene and the test scenes. Yeah, unfortunately, the videos are not available now. Okay, this one works. So another very important consideration is how much engineering efforts a particular algorithm requires. So for that end, we actually took a step back and asked us how far imitation learning from human demonstration alone can get us. So actually, the results are not so bad. Let me show this again. So with less than 1 hour of human demonstration for each task, the policy shows decent performance for a range of complex manipulation tasks. And the key here, we think, is the use of virtual reality teleoperation platform, which naturally leverages human manipulation instincts and unifies observation spaces between human and the learned policy. And currently, we're working on further exploit this platform to further improve the learning outcomes. Thank you.
Hi everyone, my name is Adam Stuke. I'm a third-year PhD student here at Berkeley working with Professor Abil. My primary interest to date has been scaling up simulated reinforcement learning, so doing mostly systems work. So what you've noticed through a lot of these presentations is that this is a really experiment-driven field. There's many good ideas of how to improve our reinforcement learning algorithms, and some of them actually work, but you have to try them to know which ones that is the case for. So we've got two main goals in this project, scaling up reinforcement learning. One is to be able to do more of the same experiments that we already do in order to have faster turnaround time, to find the ideas that do work, and the other is to scale up to bigger problems that maybe were just infeasible to run in the past, and you can maybe do more complicated and more interesting work that way. So how are we going to do that? Well, looking forward to using the modern hardware that we have today. It's all about multi-GPU computation. So NVIDIA has their flagship deep learning box. It's called the DGX-1. They put 8 of their latest and greatest GPUs in one box. Amazon also is offering instances of 8 or 16 GPUs. And the way we typically run our RL experiments, simulated RL experiments, is either CPU only or maybe CPU and one GPU. So this offers us a lot of room for growth if we can learn to fully utilize these machines for our experiments. So one example of a sort of scaling performance that we've been getting, this is an algorithm of trust region policy optimization, which either you've already heard about or will hear about very soon, playing Atari. And you'll see that we achieve perfect scaling in terms of the actual evaluation of individual functions on the GPUs, this Hessian vector product. What holds the scaling back a little bit is actually the scatter function, which is transferring data from the CPU to the GPU. So this is the sort of thing that you have to think about whenever you're programming multi-GPUs. But overall, a 7x speed up, we're feeling pretty happy about that. And soon we'll be applying these techniques to other deep reinforcement learning algorithms and hopefully have some exciting learning results to follow. Thank you.
Hi there. I'm Carlos Forenza, third-year PhD student here at UC Berkeley, working with Professor Peter Abil. My interests are training policies that can generalize to large set of tasks, and these policies, I want to train them under weak supervision, so it doesn't cost a lot of human effort. To tackle this problem, I've been working in different fronts. One was hierarchical RL, because of the promise of reusing skills that you have learned for some tasks. I've also been working in curriculum learning because it improves the efficiency on hard tasks when you have this set of tasks. You know, if you tackle first the easy ones, that will help you build skills for the hard ones. And I'm also currently working on meta-learning from demonstrations because these will allow us to use experience that we have collected from other tasks to quickly adapt to new tasks only from one demonstration. Today, I'll be talking about some work in this second point, the curriculum learning, and I'll introduce you reverse curriculum generation for reinforcement learning. The motivation is for a set of tasks that is, in general, goal-driven task. Many robotic tasks are about reaching a specific configuration from everywhere. This will be called the goal. But it's usually very challenging for reinforcement learning because it's inherently a sparse reward that you only get when you reach the goal. And all the other start positions that don't manage to reach the goal will give you a zero reward, so no learning. The approach that we took is to try to solve the task in reverse, which means first training from the positions that are very close to the goal, that will be easy to learn, and then you bootstrap this knowledge to solve from even further away. And also we have, to build a curriculum tab, we keep sampling more from the start states, from where you succeed sometimes, but not always, and this is what gets you the most efficient learning. As a result, so the red line that you see here is simply trying to solve the task and sampling every time from a different start position uniformly, and you see that it doesn't get a lot of success. If instead you solve the task backwards, you get the blue line, and if on top of that you do this extra curriculum that I was saying of sampling more often the ones that you're succeeding sometimes but not always, you get the green line, so it's a big speed up in terms of learning progress. And then I'll show you, we're applying these to very complex manipulation tasks, and you'll see a video here. This is a task where it has to introduce a key, turn it, introduce it more, and turn it again. And again, it only receives a reward when the key is fully inserted. So you can see here different instances of success of this task that are basically from any position around the robot is able to go and introduce in there. Yeah, thanks.
Hi everyone, I'm Ignacio Clavera, a first-year PhD student at UC Berkeley, working with Professor Peter Abil. My main interests are in model-free deep reinforcement learning and transfer learning, especially from transfer learning from scene to real world. And why do we care about that? Like, model-free learning is very useful because you don't have to make any approximations about the model. So you can learn in setups where you have a lot of nonlinearities and just learn directly from data. However, most of these algorithms are very sample inefficient, so it will take weeks in change in real robots. That's why it's very important, this transfer from scene to real world. This is my last paper, I submitted to IROS. It's called transfer via modularity and reward guiding. Here, essentially, what we do, we decompose the observations, the policy, and the choice that we apply. We apply the choice via a position controller, and then we get the observations from the real world via error tags. This makes the whole process much more robust in order to train just the policy in simulator, and then we transfer directly to a real world without further training. We see that the results are from simulator and real world are very comparable. So we can, by using this method, we can robustly train a policy in the simulator and then use it in the real world without further training.
Hi everyone, my name is Tanat. I'm a second year PhD student advised by Peter Bill and Stuart Russell. My main interest is in model-based RL, as like many of you learned this weekend that in order to push reinforcement learning to work in the real world, we want to be more data efficient and be able to generalize to different tasks. Yeah, so that's about the motivation behind this. In particular, I'm more interested in model-based RL in continuous control domain. And there are many challenges. One of the main challenges that I'm going to talk today is model bias. So you could imagine if your model is imperfect, your policy will learn based on that model alone, and then it will overfit to that model. And when you test your policy in real world, then it could be like crappy and like that sort of thing. So yeah, so that's my main problem. And our approach is instead of learning only one model, we could learn multiple models from our current data. And that way you could capture uncertainty in your data. So you know exactly in what data regimes that you are uncertain about and in what regimes that you are very confident about your data. And then you could do your learning algorithm on those models. And the algorithm that we use is TRPO. So imagine if we train TRPO to work well against our models, we would be confident that it would generalize to real world. And also, the benefit of this is like when you do TRPO on the models, you basically get free data from the models because you're not interacting with the real world. And here are some of the results. Unfortunately, there is no access, but the first video is on Swimmer. Basically, it's a 3-link robot is trying to swim forward. Yeah, and the reward we give is to go as far as possible to the right. The second one is like the hopper. This one is like you want to jump forward and doesn't. If you fall, then you terminate your episode. And the one on the lower left is half cheetah, where you have a cheetah like a robot and you want to run forward as fast as possible. The last one is a reacher, where you want to reach to any objects as fast as possible. So yeah, so we get a pretty good results on these 4 domains, and we are hoping to push more to like even more complex domains like humanoid or like Walker 2D. Thank you.